Hello, my name is Matthew, and thanks for coming back to my video. So in today's video, I'd like to share with you how to make different trajectories and how to make different ways for your robot to turn and how to help your robot maneuver different turns in different situations. So the objective of the VEX IQ Autonomous Challenge is to get as many points as you can in 1 minute. So that's a very big restriction. So for example, in the full volume game, you need to collect all your blocks, dump them, and get to the supply zone in 1 minute. So as you see here on the autonomous route map, this seems pretty difficult because first of all, the turns have a very sharp angle, like very big angle, and also the robot has to follow the blocks. So if the robot just walks along and then turns, it could potentially hit the block away. It needs to follow the path of the blocks. So this is why we need multiple different sorts of turns or multiple different kinds of turns to help the robot be more efficient and also more accurate. And another example is on the second turn here, or sorry, the third turn, the robot could hit the wall. So you need a certain type of turn for the robot to not hit the wall and still collect the blocks. So in this year's game, which is Rapid Relay, it's a lot more simple where the robot just walks back and forth and it doesn't need that many turns. But we still need different sorts of turns, different kinds of turns that have different properties to help the autonomous be a lot more efficient. So now I'm going to share with you the different formulas and different kinds of turns and what they can do. So the most common formula online is the positive negative turn. So that's basically just the left side going positive and the right side going negative, or vice versa. So this, first of all, this is the fastest sort of turn because both wheels or both sides are pushing to make the robot turn. One side is pushing backwards and one side is pushing forward, which could cause the robot to turn very, very quickly. So you see, as you see in the formula, left side is positive and the right side is negative. So they're running at the same speed but negative of each other. So one side could be 80 and the other side could be negative 80. So, and as the air gets smaller, or as the robot gets closer to its turn, the speed will slow down and will eventually come to a stop or near stop when the robot hits its wanted point. So this is good for a lot of turns near the end of the program where you don't need another walk, because there's a big problem when it does like a walk and then this kind of turn and then another walk. So the problem is that once you walk, you turn again, but then once you finish your turn, the robot's speed is at 0 because the robot slows down as it gets closer. So once it's finished its turn, it needs to re-accelerate to do the walk. So this could be a huge time loss and a loss of potential points. So as you just saw, as the robot got closer to its wanted angle, it started to slow down a lot and got to a halt. So here's a sample code for this turn. And one consideration for this turn is the location, because since one side is pushing forward and the other side is pushing back, let's say the right side is pushing back. If the robot's against a wall, the right side could push against the wall and it could offset the robot's angle. So then it could get stuck on the wall or it could get shifted in position. So in my previous video, we discussed how to use the walk heading and how to create the walk heading to make the robot walk straight following a fixed angle. So the WalkHeading PID can also make turns if you just do 2 walk headings right next to each other. So in this example, it says walk heading 200 at heading of 90 and then walk heading 150 at a heading of 150. So once the robot's finished with the first walk heading, it enters the second walk heading. But then since the robot's facing at 90 degrees and it wants to turn and follow 150, it uses its PID to reduce the error and turn to 150 and follow the 150. So this would be one smooth and continuous motion because the robot's still moving forward and would kind of drift out in order to turn to 150. So let's take a closer look at this formula in action. We want the robot to run as fast as it can. So in this formula, we keep the outside wheel as fast as it can, so at the maximum speed. So let's say for KP of 6 and the max speed of 80 and an error of 60, then if you plug the numbers in, max speed 80 minus KP 6 times error, which is 60. So this would be a very low number, which would just round down to negative 80, because the lowest you can go is the max speed, or the negative max speed, which is negative 80. And right wheel would also be negative 80. Positive 80. So then this would be just the same as the rotating, where one side goes forward and one side goes backwards at the same or opposite speeds. But then as the error gets smaller, in this case it would be 27, because 80 minus 6 times 27 is less than negative 80. So as the error gets smaller, the left wheel velocity would actually get bigger than negative 80. So this would cause the robot to not turn as tightly. It wouldn't be rotating anymore. It would be kind of doing an arc. It would sort of do a wider turn. So as the left wheel velocity gets bigger and bigger, when the error gets smaller, the turn would start to get a lot bigger and would spiral out. Just like a Nautilus shell. You see, in the shell, as the error gets smaller, the difference between the left and right velocity will also decrease. And that's the major factor, because the turn speed and the turn tightness is based off the difference between the left and right speeds. So as the tightness and the difference decreases, the arc which the robot follows with the turn starts to get bigger and bigger. So here's the expected path you see by using these two WalkHeading blocks. So in order to make the WalkHeading turn, you also need to test a KP that will work for both big and small angles, because there's no way to change the KP if you want to do a big or small turn. So that's one major downside. But here is how the robot would walk. So like I said, it's a lot more smooth than the normal just rotating, but it would also sort of drift out like the robot just did. It would drift out and follow 150, so that's one thing to keep in mind. So like I discussed before, one major downside of using the rotation is that it slows down as the robot gets to the wanted angle. So then this would be a major time waster. So here's the formula that could sort of counteract that and make sure that the robot doesn't slow down completely as it gets to the wanted angle. So then the behavior would be similar to what I just showed with the two WalkHeadings, where it would kind of spiral out, or it would kind of drift out and continue the turn. So similar to the Nautilus shell. So, but one big upside to this is that since it's a dedicated turning block, you can actually have a KP variable that you can input. So let's say big turns could have a bigger KP and small turns could have a smaller KP. So this would reduce the, it would make it a lot easier to code, because you don't need to go through a long process to find a good KP that will work for every turn. You can just have your own, you can set a KP for every different turn, instead of finding just one KP that would work for pretty much every turn. This gives it a lot more flexibility, and it makes it a lot easier to code. So this is the fourth kind of turn. Up till now, we've been talking about turns where one side goes forward and the other side goes backwards, which would be more of a rotation. But there's one big con, which is it could cause a jerking effect that could, one, hit a wall and cause the robot to get set off, and it can also be a little bit of a waste of time. So another way to reduce the effect is only have one side run the turn. So let's say this side is 80 and this side would be 0 or a very low number. So the reason we don't want to use 0 on one side and have a high number on the other is that if the robot speed is set to 0, if the right side speed is set to 0, it might not be able to hold the position, and the position would be off, which could offset the calculations. So maybe we could do like 0.1 or a very small number instead of 0. So in order to do this, we can use the max function in Python, which uses either 0.1 or this number. So it chooses the number that's bigger. So if this calculation is bigger than 0.1, that means it'll use this calculation. But if this calculation is smaller than 0.1, it'll just use 0.1 instead, because again, we don't want to use a negative number for the left velocity. We want to keep both numbers positive. Here's the sample code, and one big change that this does is that instead of rotating, the robot sort of rotates along this axis, or in between the non-moving wheels, instead of rotating with the center being the axis. So also another big pro is that it won't hit the wall because both wheels are technically positive, even though it doesn't look like this side is very positive. So this makes it a lot easier, and it's a lot better because first of all, it won't hit the wall, which could be used in a lot of different applications, and it also sort of follows a different axis, so you can use that in case you want to in any other application that you could use. So far we've been using a PID we've been using PIDs and the PID formula to make a turn. But does a turn need a PID at all? So look at this vehicle circling this Arc de Triomphe. So the driver is just putting the steering wheel at a constant angle during the turn, which causes the robot to go just at a certain angle consistently. So this is a lot easier to plan than a PID controlled turn. And with the WalkHeading block, it can correct the turn if it's a little bit off, because the WalkHeading will follow a consistent angle. So even if the turn is 10 to 5 degrees off, it will still correct itself using the WalkHeading if you use the WalkHeading after. So since both the left and right are at a constant positive speed, we can use this turn at the docking wall so it won't hit the wall. Like I said, both wheels are positive, so it won't back up into the wall. And also, we can plan the trajectory a lot more easy. So here's the formula. So let's say left wheel is at the max speed, so we want the outside wheel, or the one that's pushing it and doing most of the pushing, at the maximum speed to make sure it's the most efficient. And you can have a constant inner speed, so the robot's constantly spinning in a perfect circle because these two are at a constant ratio. So if this ratio changes, the arc will be bigger or smaller depending on the ratio change, because like I said, the turn is dictated by the difference between the left and right velocity. So here's a sample code for that. Having an inner speed as an input variable can create different turns, different sizes of arcs for different locations and situations. And it's also very easy to implement. And in our experience, not having a PID can reduce complexity, and the trajectory is also a lot more predictable. But you would have to have a WalkHeading after that to make sure that it continues to follow the certain angle, because like I said, it could be a little bit less accurate. So Michaela, thanks for joining our conversation.
Yeah, I'm very happy to be here today.
So what did you bring to show us today?
So I want to show you guys my experiments with the different turning styles to see and visualize how each of these turning styles can change the path and see what is the most effective.
Oh, so let's take a look.
Alright. So to start off is the very typical positive and negative turn, where one side is going positive and one is going reverse, so the whole thing spins. So our code for it just goes forward and turns and it goes forward again. So it's very robotic and it's very clean and sharp. Here, there's a video.
I see. So you can see all three parts of the turn, where the first it moves forward, and then it turns and it moves forward again. So they're all kind of separated, right?
Yeah. Although this is kind of like a little bit of waste of time, it's not the most efficient as it can be, but it's very good for sharp turns, and it's very clean.
Yeah, it looks very clean and very precise.
Yes. So the next one is the code where it doesn't really have a dedicated turning code. It just uses the built-in PID from the WalkHeading. So you can see in the video, it just turns while walking, but because it doesn't have like different KPs, it just may overturn, but the PID will bring it back.
Oh, I see. That turn looked it looked very fast, but it didn't look as precise.
Yeah.
Even though it sort of fixed itself at the end. So I'm guessing, like you said, that's probably because since there's like a built-in turning PID sort of in the WalkHeading, it might have a KP that's too high for small turns or too small for very big turns. So it seems too much to compromise.
Yeah, this takes a lot of it's not very efficient because it has to readjust itself, and it's like very different for each turn. But for a rapid relay, the navigation, it's just really simple, so it might work because the code is also very simple. Yeah. But this next one, this does have a dedicated turning code, and with that we can actually change the KPs for each turn. So that makes it like really precise if you tune it for each turn that you're making. As you can see here, this turn, this KP is too big, but because of this code that we have in the middle, we can change the KP to 2 so that it goes very direct, and it doesn't waste time on fixing its placement.
Oh, I see. So it might be hard to find a KP that works for every turn. So it might be easier to just have a different KP for different turns.
Yeah.
Like big KP for big turns and small KP for small turns.
Precisely. This is also really good to for customizing your route. Yeah. And this next turn, it's the positive control range, because usually it'll have one wheel going backwards and one going forward, but we're gonna cut down so that it only goes forward, just because when it's right against the wall, when the wheel goes backwards, then it hits, the fin will hit the wall, and that's not really good. So instead of going backwards, it won't go. It'll just set its speed to 0. So yeah, you can see it here.
Oh, I see. So both wheels are technically moving forward, and one wheel, the right wheel, is actually the one pushing the robot to do the turn.
Yeah.
So then the left wheel won't run into the wall at the back and cause the robot to get off, right?
Yes. And because we can start, and in this case with rapid relay, starting the turn from the wall makes it a shorter route than having to go forward and turn.
Oh, I see. And it looked like the turn was centered between the two left wheels.
Yeah.
So we were able to start the turn when the robot was against the wall.
Yes. So the last turn that I'll be talking about today is the differential speed turn, where it turns by the difference of speeds between the two wheels or the two sides. So one will be, for example, 10% speed, and the other one will be max. And because they're both moving forward, but one is just going faster than the other, causing it to turn, and it'll make a perfect circle. You can see here. Hello? No. Does it go? Oh, there it is. Yeah.
Oh, so I see. So it's rotating around the X mark, right?
Yeah, because it's going in a circle. So that's the center of the circle. So you can see that I've actually experimented with the 10% in the inner speed, 20% inner speed, and 30% inner speed, causing it a different difference between the inner and outer wheels. So you can see as 10%, it's very close. It turns more. 20% it turns a little bit less, and 30% turns even less.
Oh, so that makes a lot of sense, because if the outer speed is at let's say 80 and the inner speed is at 10, then the difference would be 70.
Yeah.
And then the difference would get smaller as the inner speed gets bigger.
Precise.
So the less difference means the bigger circle you have to make because you make a smaller turn.
Yeah.
Oh, I see.
So here you can put this to work in a game, just because the turn just follows a circle, so it's very smooth, and you can like use it to avoid, like, because it goes in this circle like this, the fins won't hit the wall, making it a shorter route, and it is really smooth with turning. Yeah.
Oh, that's a lot of good information. So, with all the styles of turning that you covered, which one do you use the most, or which one do you think is the best?
I personally think that this one, the differential speed turn, is the best, just because it follows a circle. The path is very predictable and easy to plan, and it's also a lot more it's more efficient than the PID turns, because they're both moving forward at the same time and they're moving forward. So it uses that energy instead of holding back. And it just makes the trajectory planning very easy, and it's also very simple to code.
Oh, I see. So, thank you for joining us in the conversation and sharing all your tests.
Thank you for having me.
So, in today's video, we reviewed different formulas to help your robot turn, different properties of each formula, and different trajectories that they do. So with this in mind, can you create your own trajectory and your own formula to make your robot do what you want to do? So this is my last video before the end of winter break, and I hope I've shared with you enough information to help you create a nice autonomous. Thank you guys for watching.